Let's design a one-pole, low-pass RC filter with a corner frequency of 500 Hz. In other words, this filter will pass low frequencies, and then right around a frequency of 500 Hz, we'll start to have a 20 decibels per decade roll-off. What this means is that when we get out to about 5 kHz, we should be about 20 decibels below zero. This is what the prototype circuit looks like for our one-pole low-pass filter. We learned that for this particular filter, the corner frequency is at omega equals 1 over RC, where RC is the time constant, or tau. By the way, a common point of confusion here is that tau is the time constant. It's not the period, say, of a periodic signal or a sine wave. They both have units of seconds. Omega equals 2 pi divided by the period, and that's a bit tricky. It's the frequency that's related to 1 over the period, but here the omega is related to 1 divided by the time constant. So the point here is don't get time constant confused with period. They're two completely different things. Here, time constant is R times C. Omega is 2 pi times the frequency, therefore the corner frequency, which I can indicate with a little f naught, is going to be 1 divided by 2 pi RC. Frequency is the variable, so the filter will of course give a response at all the other frequencies, but this one particular frequency is special because right at that frequency, half the power is going to get through. It's the 3 dB frequency, or the frequency at which the response is 3 decibels below zero. Now let's look at our corner frequency here. It's supposed to be 500 Hz. That's in the audio range, so I'm going to choose a 100 nanofarad capacitor to put the resistor in a good range. We'll see if it works out. I suppose if it doesn't work out well, we can always go back and change this choice and then recalculate R. Let's change around the formula to solve for R. If I plug in 500 Hz here for F and 100 times 10 to the power minus 9 for the capacitor, then I wind up with a resistor R. I think it worked out pretty well. We don't want a resistor that's way down deep into the ohm range, like 10 ohms or 20 ohms, and we don't want resistors to come out super high, like 10 mega ohms or something like that. Tens of kilo ohms, that's good range, so we'll stick with this choice. Keep in mind though, that if we use this filter in a circuit and the load is somewhere in the neighborhood of R, then we might start to have a problem. If my load, for example, were hypothetically a mega ohm though, this filter would work perfectly well and the corner frequency wouldn't be altered. Let's look at another example now. Let's design a one-pole low-pass RC filter with a much higher corner frequency. In this case, we're going to be designing it at 1 megahertz, and that's radio frequency. It's right in the middle of the AM radio spectrum, by the way. Sometimes I like to write RF when I'm talking about radio frequencies just to save space. Here's our prototype circuit. 1 resistor and 1 capacitor, just like with example 1. The difference here is that I need to choose something smaller for our capacitor so that the resistor then works out to some reasonable value. Hundreds of picofarads. Now if the capacitor is too small, like say 50 picofarads or 100 picofarads, then that's not very good if you intend to build the circuit on a breadboard because the plate-to-plate capacitance on a breadboard is in that neighborhood, so we need to avoid that. I'm going to choose here a capacitance value of 500 picofarads. Our corner frequency for this filter is given by 1 divided by 2 pi RC. Let's rearrange this equation to solve for R. When we plug in 1 megahertz, or 1 times 10 to the 6th power for my frequency, and I plug in 500 times 10 to the power minus 12 for the capacitor, I calculate then that the resistor needed is 318 ohms. It's a fairly small resistor, but we started off with a fairly small capacitor too. That's just the nature of working at high frequencies. As the frequency gets higher and higher, the components necessary to make the filter work at that frequency are going to get smaller and smaller. I think this resistor is still in a very reasonable range considering that the frequency is so high. In example 3, I ask what component should we use in series to block radio frequencies but allow a DC control voltage to pass. In fact, we should use an inductor, and let me tell you why. An inductor has an impedance of J omega times L. So right away we can see that this omega is somehow included. If the omega is very, very small, or we're getting close to the DC values, then it's almost like the inductor is not even there. The signal can go right across it. However, as the frequency gets higher and higher, then the reactance of this inductor, or the impedance of the inductor, gets larger and larger, and that effectively blocks the signal. So typically inductors are used for exactly this reason. We can put it in series where any signals might pass, and the high frequencies will be blocked, the low frequencies will get through. Quite often the application is to block noise. I'll show you an example of where it's actually used. You'll often see these things in power cables. If you ever have, for example, various computer cables, you can often see these cylinders near the ends. Right here we have an inductor. They call it a choke, or a high-frequency choke. It chokes off the high frequencies, and usually these things have inductances in the neighborhood of a few millihenries. In example 4, I ask what component should we use in series to block DC but allow the AC signals to pass? And of course, this should be a capacitor. The omega here is in the denominator. So as the frequency gets higher and higher, the whole fraction kind of starts to look like 0, and it's almost like the capacitor's not even there. The high frequencies just zip right through that capacitor. The low frequencies, however, are completely blocked. Remember, the two plates of a capacitor are nearby one another, but they're not touching each other, so you cannot flow a DC current through a capacitor. It's completely blocked. In fact, this use of a capacitor to block off the DC signals is really common. These blocking capacitors typically have values between hundreds of nanofarads all the way up to hundreds of microfarads. Those are the typical values that you would run into for this particular application. One thing about the filters that we've just looked at, especially those in examples 1 and 2, and something that I mentioned in the last video, is that if you hook a load to a filter, you can change the performance of that filter. Or if the source giving a signal to a filter has characteristics that might change, then the filter's performance could be affected. In the next video, we're going to look at how to specifically prevent this problem. We're going to look at buffers.